Thank you so much for the invitation. It's been great to visit University of Washington. Actually, this is my first time visiting the campus, and very excited to meet, your very excited students. So take a good care of them. So I wanted to give a talk that kind of illustrates how math and and physics come hand in hand. And I had a little bit of hard time of deciding which topic to choose, because in my group, so we do research in several areas. So one is active matter, and the others are, I just wanted to highlight before I get going, we do research in math biology, where we're looking at the membranes that are enclosing cells and cellular organelles, and these membranes are actually fluid. So there is a great interest of understanding dynamics of membranes and how they undergo phase transitions and how this is related to signaling. So my group has been working on that for a while, and so like for example in collaborations we are running these massive MD simulations of biomimetic membranes. So these are closed lipid bilayer membranes. As you can see, they're constantly fluctuating, so there is a lot of thermal noise involved. And so our group has been developing both continuum and kind of stochastic models of understanding the dynamics. And most recently, this is a project that led us to, I don't see where it is. Okay, it's a very tiny dot. The study of membranes brought us to the to the study of the action potential, for which we got this recent award to actually study and look at the action potential from the perspective of a nonlinear wave in a two-dimensional fluid, the biomembrane. So I'm very passionate about fluid dynamics as a classical example of applied mathematics, and so I've been trying to convince people that fluid dynamics is not just pipes and whatever Poiseuille flow and planes, but it's actually very much alive and very much relevant to understanding the world. Another part that we are very interested in is actually stabilities and pattern formation, in particular electric field induced instabilities. And this is just one video of what's coming out from our lab. So I direct the applied math lab at Northwestern, where we're looking at a droplet, which is in electric field, and we're looking along the field direction. So what you're going to see is that the droplet initially is going to become like a pancake, so the radius is going to increase, and then it's going to undergo kind of an interesting instability, so it's going to start shedding rings. And so this is where the moment happens, and these rings actually break up into tiny droplets, and this is a phenomenon called streaming that we've been studying for a while. And this can lead to this little, now you're looking from the sideways, so when you turn the field out, the droplet jumps back to being an equilibrium sphere, and the rings remain around it, so you got your own Saturn ring, Saturn planet in the lab. And so if you're interested, I'm more than happy to talk about all these phenomena, but for the purpose today, I just wanted to kind of bring to your attention a field which has been rapidly evolving in the last 10-15 years. So first of all, do you know what active matter is? How many of you know what active matter is? Okay, good. Then you're going to learn something today, for those who haven't. And and then one other thing that you're going to learn is what is this Quincke Rotor. So it's my favorite particle with fancy nonlinear dynamics. And before I start the presentation, I wanted to acknowledge that this is a collaborative work, thanks to many students and postdocs in the lab, and it's an ongoing collaboration with Argonne National Lab. And for those who are also looking for postdoc opportunities, please check out the new Institute on Math and Theory and Math in Biology. So the fellowship application is, a deadline is coming shortly. So this is not a bio talk, but if you're interested in action potentials and biomembranes, you can talk to me regarding postdoc there. So what is active matter? So active matter is kind of a driven system as a collective of units that are self-driven, so self-propelled, like birds or sheep or fish, and even humans. And what is fascinating about this system is that now if you have all these self-driven units coming together, interesting emergent behavior occurs. So in the case of the starlings, so these are the little birds, what you see here is the birds kind of flying together in a very, forming a very large-scale coherent motion. They don't bump into each other, so, and, the flow is kind of beautiful and self-organized, but it's not globally driven, so it arises from the local interactions between the birds. So the birds here, one bird here doesn't know where, like the bird on the other end of the flock is, and yet somehow they manage to move together in a very coordinated fashion. Fish, I'm scared to turn these videos, but here is if you Google YouTube active matter videos, you're gonna see a lot of that, and then this kind of starts with a very idyllic picture of sheep herding in Scotland, I guess, or something. So you have the herd, and then when you zoom out, so you have all this. So I don't want the sound. They also move in a very fascinating way. So they're going to start running around. And then again, it's a large-scale coherent motion that emerges from the local interactions between the units. So why is it became interesting? So it's because actually these are very different systems, but somehow they're described by, they exhibit the same generic behavior, same universal behavior. So there has to be some sort of abstraction from the physics, and that's where math kicks in. So can we come up with a minimal model of flocking? And that's what Vicek did in 30 years ago. So he created this minimal model for the flocking, which is purely mathematical. So you have a bunch of particles that have preferred direction of motion, so they're what they call it polar, and so they move with a certain speed and a certain direction, and then each time you update, they move a time step, so they update their position based on the average orientation of the neighboring particles. You can think of them as spins. So they see that only neighbors in a certain radius are, and then there is a noise, and then you update the position. And what this model showed is that if you depending on the noise level and the density of the particles, you actually can form flocks, and what was also interesting is that actually you can think of this, and what he proposed is that you can think of this behavior as phase transition. So you're going from, like, when you have a lot of noise, there is disorder, but then as the noise kind of comes to the right amount, you transition to a very highly ordered state. And that's in 95, few years later, physicists kind of jump into this, like, oh wow, it's great. We can think of flocking, swarming, collective behavior of humans, of traffic, etc., from the perspective of statistical physics. And and then there was a lot of effort put together to kind of develop tools of statistical physics to describe active matter. So what I will try to convey to you, to try to convince you today, is that statistical physics is not the answer of it all, just like machine learning is not the answer for all problems and modeling problems. And there is a lot of room left for, especially for applied mathematicians, to contribute to the field. And where these opportunities occur, they occur in the field of so-called wet active matter. This is where I'm very interested. So instead of looking at birds and sheep and other animals, I'm looking at the microscale, like the bacteria swimming. So what we are seeing here is examples of, this is an E. coli kind of swimming around in a solution. When you have a lot of these bacteria, when the density increases, you see a similar, kind of qualitatively similar behavior to the flocking of the birds. And then also other more interesting things like very, very, very dense suspensions of bacteria exhibit this very chaotic flow. And to someone who does fluid mechanics, by the way, how many of you know fluid dynamics? Okay. So there is the phenomenon of turbulence where the flow is very chaotic, but it's usually associated with inertia. So you have to be at very high Reynolds number. And here we are on the scale of the bacterium. So we are at micron scale where inertia is not important, yet you end up with chaotic flow. So the question is, where does it coming from? There is also some more exotic bacteria, such as this spinning bacteria that forms crystals and so on. So we see this self-organization arising in this microscale system, and the question is, can we study them in a very controlled manner? So the turbulence actually was a very big question in the question of active turbulence was still ongoing, very debatable phenomenon. And the problem with it was that it's very hard to work with bacteria. They need oxygen, they multiply, they die, they create goo. So it is quantifying the flow with very well-defined activity, density of the particles, etc. It's very hard to do, and so that's why we got into this business. It was like, okay, let's create an experimental platform, a system that can allow us to actually study collective dynamics of particles that are embedded in a fluid and kind of focus on this very important aspect. Well, does the fluid matter? So, on the microscale, we know that if I move here, it's going to be known to the whole world. It's like swimming in honey. So viscous fluids transmit stresses very quickly. So, does hydrodynamics matter? And the answer is yes. But let's start first with the attempt to create active particles so that we can use them in the lab. There's been actually this is a very funny field because there is a lot of theory and there is a lot of models, but there is relatively few experimental systems. Some of those are given here. So the original active particle, one of the original ones was like a direct mimic of bacterium. So they just basically attached a flexible magnetic polymer filament to a bead, and then with rotating field, they created non-reciprocal, like a corkscrew motion, so that the guy propels very slowly, but still moves. However, this kind of design does not lend itself to kind of large, studying collective dynamics, because producing a lot of these guys is just impossible. There are some other ideas. So there's people using chemical particles, electrically driven, and so on. So, what we are gonna, and what I'm gonna present to you is a particle that even applied mathematician can do experiments with, and that's the Quincke Rotor. So this is a particle that it's actuated by a torque that is created by an electric field, and if it is sitting on a surface, this torque makes the particle roll, so it looks like it is self-propelled. So we're using the electric field to energize the particle, but the electric field have no impact on the determining the direction in which it is going. Other people have also used magnetic fields. We like the Quincke Rotor for several reasons, and I'll go through them here. So what is a Quincke Rotor? Well, as the name suggests, some guy Quincke, shortly before the 1900s, so 100-something years, 130 years ago, noticed that a dielectric particle, when exposed to a uniform electric field, spontaneously started spinning above a threshold electric field. There was a symmetry breaking, which made the particle from being still to spinning. So what do we mean by symmetry breaking? So you have a base state when you turn the field on, the particle polarizes. Since it's exposed to electric field, ions kind of accumulate on the surface. There is an induced dipole. So this is like physics, whatever, 101, but you have this induced dipole that is anti-parallel to the field, and everything is symmetric. So they're all pointing in the same. They're along the same. They're collinear. However, above a critical electric field, actually this spinning occurs. So suddenly the dipole becomes tilted relative to the electric field. So, and it is steadily tilted. What do we mean? So suppose it perturb a little bit the dipole. Well, if you perturb the dipole, there is a torque, P cross E. The dipole cross product with the electric field gives you a torque. That torque wants to rotate the particle. And if these charges were attached to the particle, the dipole will simply flip, and that's the end of the story. However, the situation is such that these charges are not bound, they are free charges. So, as these charges rotate with the particle, more charges in terms of current are coming from the bulk. So you have a steady state in which the surface current during the charges rotating is balanced by the bulk current coming from the solution. So you can think of it as the water wheel. So imagine these are all the buckets. How many of you have seen the Strogatz video with the water wheel in chaos? Oh, guys, applied math? Well, then go watch it, but imagine that these are all little buckets, and then you're pouring water, like a liquid on top of it, and you're filling the buckets. So at some point there is the instability which creates the rotation. And now if this particle is on a surface, it's going to start roll. So we have actually a state in which the particle is translating. Sorry, this is a little bit funny. What is valuable for us is that actually this is a system with memory that's going to become important. So there is a finite time to charge and discharge the particle that depends on the permittivity and the conductivities of your materials, the particle and the solution. Then there is a very well-defined threshold for the instability, for the onset of rotation, and that depends on, again, material properties that you can tune in the experiment. And then the rotation rate is set by the electric field. So that means that how fast this particle is spinning or rolling, you can control by tuning the electric field. So you have control over the activity. And finally, the direction of the rolling, which is set by the direction of the torque, is randomly chosen from all directions in the plane perpendicular to the electric field. So the direction of rolling is degenerate in the plane perpendicular to electric field. So therefore, there is kind of randomness in which it is chosen. So we have, there is a possibility of actually random reorientation by turning the field on and off. So why is it valuable for us to create active matter? So before I get there, I wanted to give you a fun fact. So I mentioned the water wheel. So if you take nonlinear dynamics and chaos, etc., so you're familiar with the Lorenz chaos. So it turns out that the Quincke rotor is one of the few physical realizations of Lorenz chaos. If you take the equations of motions, which is the conservation of angular momentum and the polarization relaxation, you can actually map them with a kind of a smart transformation exactly on the Lorenz equation. And one can look at the bifurcation diagram. I mean, it's well known in chaos theory. So you have the rotation rate is a function of the field strength. So there is first pitchfork bifurcation at parameter alpha equals to 1 when you have a transition from no rotation to steady rotation, either clockwise or counterclockwise, depending on the perturbation. And then at a much higher field, you enter the kind of the chaotic regime. So there is a Hopf bifurcation, and there is various regimes, chaotic, period doubling, and so on. And the dynamics becomes much more fancy, and we can see this in the lab. So this is a video of our Quincke rotor under the microscope. So this is a 100-micron sphere. We see these little defects. So this is just a plastic sphere with some literally defects, but they help us to visualize the rotation. And above the pitchfork bifurcation, you have a nice steady rotation. If you go to much higher field strengths, actually you see the chaotic rotation. So it's going forward and backwards in kind of irregular fashion. So I like this to show this that Lorenz chaos is real. And okay, so So coming back to active matter, so the Quincke Rotor has become a super popular model system to study active matter, because now this Quincke Rotor, well, to start with, it flux. So this is a bunch of these rollers that have assembled into kind of propagating wave. This was the original experiment from Denis Barthelot's group in 2013. So this is a racetrack. So this is like a channel where you initially everything is randomly sprinkled, these Quincke rollers, but then over time they self-organized into this, kind of to form this directed motion. And again, each particle here is like 2 microns, and this is a length scale of 5 millimeters. So we have, 3 orders of magnitude difference in the scales. If you put them in now circular confinement, so instead of parallel confinement, but you put them in circular confinement, they form these funny waves and eventually settle into vortex. And this is stuff coming from our group, which I'm going to talk today. So the first thing I wanted to discuss is, and we'll see how far we go with the time. So there was 2 questions I wanted to address. Can we use the Quincke Rotor to create a bacterium-like entity and study the collective dynamics of bacteria in a very systematic way? Well, in order to create bacteria, we need to mimic the locomotion, the individual locomotion. So bacteria swim in all sorts of different patterns, but the most common one is the run and tumble. So they run for a while and then they tumble, they randomly reorient, and then they run again, and so forth. And so the big question in bacterial self-organization is, how does the collective dynamic, does at all the collective dynamics depend on the pattern of the random walk? And the second one is, can we do active turbulence? So what is run and tumble? It's just active diffusion. So, in normal thermal diffusion, so you have these little particles that are kind of agitated by thermal noise, and each one of them is diffusing, depending on the size. So for a micron-sized bacterium-like particle, you have a very low diffusivity. So bacteria invented swimming in order to get to food faster, because otherwise they're going to die if they rely on a plain diffusion. So they execute this run and tumble, and now you have this active Brownian particle. So the particle is swimming with a certain speed in a certain direction, and then reorients with a certain rate, and randomly subject to a Gaussian noise. So you end up with now effective diffusivity, which is set up by the swim speed and run time and the reorientation time. And now this is much faster, so the bacteria get some food. And can we do active Brownian particle like bacteria in the lab? The answer is yes. So you can take advantage of this randomization of the fact that the direction of rolling is randomly chosen upon application of the field. So now if you imagine you turn the field on, so your particle starts rolling. You turn the field off, so the particle stops. So when you turn the field on again, the particle is free to choose a completely new direction. And so if you keep doing on and on, you end up with your particle executing a random walk. So this is, for example, and you can have actually a fun system, because you can control also how correlated this random walk is, because you have this memory time. So the stop time, the time over which the particle is motionless, if it is much longer than the memory time, the depolarization and polarization time, then you have a completely random walk. But if your stop time becomes comparable to the memory time, then the walk becomes more and more correlated. And so this is what we call the ballistic swimmer. So it is completely correlated, so it's going in a straight line. Is there a question? Yes?
So the reason you have memory is because the surface gets charged And then also the mass and all that.
It's only charge. So it's a finite time to charge the interface and to discharge the interface. So for the current to supply the charges to the interface, and for the charges to kind of follow the current into the bulk. So there's no inertia in this system. Good question. Yeah. And so we have a super swimmer because these guys they roll with the speed of millimeter per second. So if you're 10 micron particle, moving with millimeter per second, so you're going 100 times more, 1,000 times more, like your diameter per second. And so it's a very active swimmer. And now you have a toy system in which you can explore different random walks. So what we saw here was a classical random walk where the stop time was the same, the run time was the same, but actually you can now mimic run and tumble. So for run and tumble, the run times are exponentially distributed. So there is a PDF which is exponential in the run time. And what you can do is create a signal. So you derive the runtime from the PDF, and you create a signal with different runtimes that follow this probability distribution function, and now you have your random walk. What's the difference between a run and tumble and the classical random walk? Well, now your particle is actually free to explore much bigger space. So if we are looking at, so now I had to zoom out this is the field of view of the microscope. This is our, 100 micron particle, which is just going around and exploring. And you can, crank up this, this game a lot. So you can do Levy walks, for example. So you can illustrate in experiment super diffusion and subdiffusion. So in that case, you take PDF of the run times that it's a power law in time. And in that case, again, you see the mean square displacement can be either super diffusive or subdiffusive, depending on what power you choose here. And you see this characteristic Levy walk pattern. How many of you have worked with random walks? Good. Does this look familiar? Levy walk? It's kind of fun to see that it's not just a mathematical concept, but actually you can put it in the lab. And then the final question is, fine, we have managed to realize the individual locomotion. Let's get to the point of how does the individual locomotion impact the collective dynamics. And that's where the zoo becomes, because we saw that when the Quincke Rotor was a ballistic swimmer, so when it was just going in a straight line with steady electric field, it was only flocking. That's it. Now, actually, depending on how correlated the walk is, so this is just what we are doing here is the runtime and the degree of correlation of the random walk. So we're just comparing the stop time versus the memory time. So here we're having very correlated walks. Here we are having very decorrelated walks. And what you can see is, for example, in you can see situations like when these particles have self-organized into rotating clusters. Again, there is no boundary here. This is just the field of view of microscope. You can have clusters. So there's what we call them dynamic clusters. So obviously there is so in this kind of system, what you see that the structure is definitely inhomogeneous. There is a characteristic kind of scale for the particle clusters, but these clusters always exchange members, and under different conditions, you can also have the situations when you have clusters that are non-dynamic, so they always keep their neighbors. So you have this slug scrolling through the thing. So bottom line, and this is just one little knob which we touched, which is the memory, the degree of decorrelation of the random walks. And we are currently working on kind of exploring how different random walks can generate different collective behaviors. So this is only one slice of the phase diagram with only one particular density. So what happens if the system is more dense or less dense? Lots of things happen. So how do we understand these dynamics? We don't. And I can tell you the short answer is that we tried to adapt the active Brownian particle model, which was the run and tumble, the random walk with noise and so on, to try to model this behavior. The answer is it doesn't work. And so the working hypothesis, right, is that actually, since the system is fluid embedded, fluid dynamics is very important. In addition, these are particles that also interact electrostatically, so we need to introduce the electrostatics in the model, in the interactions. And so bottom line, it's very challenging. So it was too many equations to show in whatever, 5-10 minutes. So, but I'm happy to talk to you. There's lots of opportunities for modeling. The failure of the active Brownian particle model, I decided to illustrate on another example, something that we stumbled in the lab. But before I switch to that, is there any questions about the random walkers? Yep, no? No. Okay. So for the time being, just take my word for granted that active Brownian particle that is usually used for dry active matter doesn't work for Quincke random walkers. And we'll see this in a second. And because it's just easier to digest in that example. And that particular example is if you, instead of the random walker, so we played with the random walk in unbounded space. There was no boundaries, there is no confinement. So we said, okay, let's go back to the basics in order to understand kind of maybe a little bit better the modeling of the walkers, is that, okay, let's keep them to be ballistic swimmers, but confine them. So, you know, we saw that if you have the Quincke random walkers in a solid confinement, they form a vortex. And we was like, okay, let's try to model this and understand this a little bit better. So why do we care about confinement? So confinement also in active matter is important because bacteria, so if you take bacteria and you put them in a droplet, so this is a droplet which is sandwiched between two slides. So it's kind of like a very fat liquid bridge. So remember when you have, you know, in unbounded space, bacteria were swarming. And now suddenly, in the presence of boundary, they form a vortex. So boundaries do impact the emergent behavior. So now what is important here is that the droplet has a very high surface tension, and the bacterium is very weak swimmer, so it cannot deform the interface. So the interface basically acts as a solid boundary. So now if the surface tension goes very little, weird things can happen. So this is bacteria that are confined in something called vesicle. So vesicle is just a lipid bilayer membrane with extremely low tension. It's like a balloon. And you see that this thing goes crazy. And so we were looking at these things and we got inspired by some now a bit old simulations which showed that if you actually put microswimmers, if you put active particles inside of a deformable boundary, actually this whole container starts moving around. And so the prediction was that it follows kind of ballistic and then diffusive behavior. So we thought, okay, so there is a nice prediction for the fact that deformability of the boundary should lead to some net motion of the container. However, the existing experiments were not seeing it, either because you had many swimmers but solid boundary, or you had very soft boundary but just very few swimmers, not enough to push this thing through. So can we have a system where we have many swimmers, very active swimmers, that can deform the boundary? And the answer is the Quincke Rotor. So that's, you know, like the answer of all our prayers, or my student prayers. So what happens now? Imagine you have the Quincke particles. So these are these are little spheres. They're sitting on the electrode in a very fat liquid bridge. I mean fat meaning that diameter is about 1 millimeter, but the gap is very small. So it's comparable to the diameter of the particle. So it's about 100 microns. So when you turn the field, so when you're looking from above, this is what you see. It's just a without activity, it's a circular boundary. And if you now activate them, so if you exceed the threshold for Quincke rotation, they all start rolling around. And what do you see? What do you see? First of all, that the shape the contour of the droplet. This is a quasi 2D droplet. Changes, so it starts fluctuating. This is the flow, and this is the vorticity. And then what we see here is actually that the Quincke's, they generate this kind of a vertical-like flow, but it's accompanied by very strong fluctuations. And then the next question is, okay, great, activity creates shape fluctuations, but nothing interesting is happening here. This thing is just wobbling in one place. What if we just crank up the activity? The activity is by increasing the field strength. Well, let me just explain what we're seeing here. So in this video, what we're going to see is we're going to track with the red line the center of mass of the droplet. The green line is just the maximum extension of the droplet. So at very high activity, so the guy is just, exploring around, kind of swimming around, not swimming, but it's trying to do almost like something like flying. And in this moment, its wish comes true. So there was a symmetry breaking, and although you cannot quite well see it from the video here, actually the vertical flow inside of the droplet actually breaks into two counter-rotating vortices, and they're responsible for this kind of wings, like formation of the wings and propulsion of the droplet. So what's going on? How does internal activity translates and gives rise to kind of net motion of the container? So I don't have to convince you for the practical applications, but hey, it's a nice way to deliver things. So if you can just something that is autonomously moving, then by internal activity I can load it with some practical useful thing and cargo, so I can deliver it from one way to another. From mathematical point of view, we have interesting problems such as how does the interplay of the internal active flow with the deformable boundary gives rise to the net motion. If you pay attention, actually, you can see that actually there is, so when the droplet moves, it leaves a trail of oil behind it, so it's kind of a memory of itself. And what we saw here is that the droplet is actually slowly pushing, it's executing a random walk, but it's kind of pushing the boundary of explored space. So there is a lot of aspects to kind of like mathematical concepts that one can study in the context of the system. I'll just focus on the motion. And that's where we hit the wall. So I had a fresh PhD student who came to me. He was like, oh, okay, I want to do modeling of this active system. I was like, well, let's take the active Brownian particle model, which is, all our particles are swimming with certain speed, and then they reorient because of noise, thermal noise. But we also put some interactions. So it was like, fine, the hydrodynamics is, I'm a fluid dynamicist, I see hydrodynamic interactions in everything. It's like, we have to put the hydrodynamic interactions. This is a quasi 2D system. So basically, in the far field, these guys are looking like potential dipoles, if you know what I'm talking about. But okay, we know what the flow is. So we just superimposed, kind of linearly superimposed this far field of each one of them. And we said, okay, let's see what's going on. Are we going to get motility? And the answer is no. So depending on the strength of the interaction, so when you have a lot of interactions, these guys are stirring each other a lot. So you end up with them kind of just being all over the place inside of the droplet. When the interactions are kind of, order 1, you can form the vortex. So all of the particles kind of accumulate near the boundary. If there is no interactions, all the particles just go to the boundary, hit the boundary, and that's the end of it. They kill the vesicle. But the important kind of outcome of this project was that we didn't see any motility of the container. So even though the boundary was deforming, because there was no feedback by the boundary on the motion of the particles, so there was no kind of communication between the boundary. Like the boundary was just, I'm running to the boundary, I see the boundary, I run away from it. Obviously this did not, serve the purpose. So the question is, so can we do better? Can we develop, let's take a step back and bring the physics into the mathematical model. by the way, this was a year of the of the research of my poor student. But but to his credit, so he was a pure math undergraduate, coming to a PhD, and so he worked on it. It's like, oh, this is math enough for me. And then after this 1 year, he realized, oh my God, I need fluid dynamics. I cannot solve this problem without understanding the fluid dynamics. So he took tons of fluid dynamics courses, and the results are going to be presented today. So why does fluid dynamics matter? So how many of you are familiar with creeping flow, zero Reynolds number flow? Few of them. Okay, so then you know that in zero Reynolds number, when inertia is negligible, the motion of particles generates very long-ranged fluid flows. So if you have a point force, so like for example, particle that is sedimenting, this is the Stokeslet. So you have a flow which decays 1 over the distance. You can have a spinning particle, a rotlet, or actually if you have a force-free particle, a force-free and torque-free particle. This is the so-called stresslet, and that flow is actually a very good approximation to the flow generated by the bacterium. So the bacterium, because the flagella and the head, they're pushing the fluid along the axis of the bacteria, and then they're pulling the fluid in the direction perpendicular to the axis. So that's the kind of a flow. And so why I was convinced that hydrodynamics does matter, because before this project, we worked on self-organization of spinning particles. And for spinning particles, if you have no fluid, they don't communicate with each other. There is nothing to tell them that, I'm spinning here and you're spinning here. So if there is no fluid, if there is no hydrodynamic interaction. The moment you turn the hydrodynamic interactions on, they become aware of each other. And so I remember... So the video is not working, but if you have two spinning particles, they actually cooperatively propel. They start swimming together, and if you have many of them, so for example, you can end up with this kind of gas of stirred spinning particle. And this is purely from hydrodynamics. If there was no hydrodynamics, they would be frozen. So, and then we said, okay, fine, let's focus on the hydrodynamics and go back to the basics. Ask a very simple question, and that's what we call it the reality from the model. Oh, in the model we have, a droplet with, gazillion of these active particles. Let's go up to the basics, and we're just going to look for droplet with one particle, and the droplet is only slightly deformable, so that I can treat everything analytically. I'm a pen and pencil person. I like to work with asymptotics so that I can get physics, insight from it. So the assumptions are going to be, we're going to be looking at a spherical droplet that has one active particles. I'll just flash the equations for just, appreciation. And so you're going to look at your E. coli or bacterium, which is located at a certain location, and we're going to ask, okay, this particle is generating an active flow, so I'm going to compute this flow into the domain of the droplet, but then I have to also, it gets transmitted in the exterior, so I have to solve also for the flow outside in the whole domain, and I'm going to ask the question, how does the presence of the droplet interface impact the flow? It's a non-trivial problem, because in order to solve the problem, you have to, kind of move the flow. You have to kind of re-represent the flow due to the swimmer from the coordinate system, which is centered at the swimmer, in a coordinate system centered at the sphere. That's a similar problem if you do like in gravity. So if you, like for example, what is the gravitational field due to the planet Earth, when it, the force due to Earth when it is like it's 1 over r squared in the coordinate system located on Earth. But what if I change it in a coordinate system centered in, let's say, the sun? So it's in many body gravitational interactions. So you do this re-expansion, and things get really hairy. So there is a lot of spherical harmonics. I'm a big fan of spherical harmonics. But you can solve the problem analytically. You can get the velocity field. What is fascinating is that while in the coordinate system of the swimmer, your velocity field has let's say, stresslet has only one harmonic like think of it as Fourier component. Once you expand it, you excite all of them, so that means that the shape of the droplet is not going to be ellipsoid. It's going to be something who knows what, depending on where the swimmer is. And you can compute the shape, assuming small perturbations. So what's going on? So we're almost done. So these are some illustrations of what's happening with the active particle inside of the droplet. If you take a stock sled, the stock sled generates a flow. The structure of the flow depends on the orientation of the stock sled, the point force. If it is axisymmetric, the flow is also axisymmetric. However, if the stock sled is kind of misaligned with the line of center with the droplet, you actually also generate rotational flow. The droplet moves, nothing surprising. So this is a forced particle. So if you have a force in the system, that means the droplet is going to move. The interesting part is that now if you consider force-free active particle, force-free singularities like the Rotlet, it's a spinning particle. So we know that usually boundaries, when you have boundaries, spinning kind of couples to translation. And something like this happens here. So you actually end up with a spinning particle, and this spinning particle generates a flow that pushes the droplet. And finally, what is relevant for our problem is the bacterium inside of a droplet. So the bacterium, we model it as a stresslet. So the stresslet, depending on the axis of the stresslet, so you can move the droplet in different directions. So this is where the stresslet is aligned with the center of the droplet, so it moves here. If it's perpendicular, actually moves in the opposite direction. And if it is at the general direction, it moves in it's generally the droplet direction is misaligned with the direction of the stock sled. So why does the droplet move? There is no force. The particle is force-free. It all comes because of the boundary, because the stresslet generates a flow, and this flow actually creates a surface flow here, which is non-axisymmetric. So it's like a streaming flow, and pushes the fluid around, the external fluid around the droplet. So you end up with the net, like something out of nothing. So the activity gets transduced to a net motion of the container. And then the hope is that the next steps of the project is that now this was a fixed one, and we're working on this idea is that now imagine you let this guy free, so let it swim. So now it's going to jump and reorient too. So that means that depending on where it is and how it's oriented, this droplet is going to execute a random walk. You can also imagine, more engineering approach, like envision that you can have, for example, some means that you can steer your swimmer to go in the direction it goes. Then you can direct the motion of your container. And finally, the dream is that actually to put many of these stresslets and singularities together and see how they interact with each other and the boundary, and then eventually predict the net motion. But that's a very hairy math, so this took good 2-3 years of my student to get through all the math. So hopefully the next one is going to work on the and these are the simulations, many body problems. So I'll just finish with kind of a summary of the results. I think we have a very it's a very easy to work with experimental system to study kind of the physics of active matter and develop mathematical model for it. It's really easy. So, and no one got ever electrocuted in the lab. There are many, it's a system is so rich and there's so many open problems. And as I told you, we are just finished with one particle in one droplet. So now you can see where we are going next. We want many droplets. I'm very interested in these very large fluctuations. So, so this is another view of our Quincke droplet, which kind of illustrates. There is no, again, this is just the field of view of the microscope. It's a free space, but here it visualizes how the particles are, what they're doing. So internal activity, large fluctuations due to internal activity are very interesting in biology. So this is something else that we worked on vesicle, which is filled with active cytoskeleton. And the dream is that eventually actually you can make active matter useful. So right now it's a very kind of a curiosity-driven research, but maybe, we can go from this guy to this guy. So we can have a real synthetic robot that is chasing after this bacterium or whatever you want him to eat. So thank you so much for your attention. Oh, I forgot. I wanted to advertise also 2 schools for the students and the postdocs. If you're interested in learning more about geometry and topology in soft matter, come to Boulder next year. The application deadline is January 15th or something. I'm teaching complex fluids and membranes, so differential geometry and dynamics on whatever, which I didn't touch very much here. And also there is another summer school in a very nice location in the Corsica Island, which is on active and autonomous matter, so how, the study of this system. So again, thanks again. Questions? Few minutes, sorry, I ran over a little bit time.
So in the droplet one you were just showing at the very end, the membrane has no mass and is fully porous, like fluid can go through.
So actually this is, this is just a liquid bridge. So this is air. So there is only air. Mm-hmm.
I meant in the mathematical model, the one with
the active Brownian particle, or this one?
The one right here.
Yeah. No, it's not porous. This is just a fluid droplet. So we are imposing continuity of velocity and continuity of shear stress and normal stresses. So it's a classical fluid dynamics problem, but in contrast of usually we solve when the flow is externally imposed, now we have internally imposed flow.
But there's no elasticity equations for the membrane?
Just surface tension. It can be, actually this is a very good question because we did the problem with adding surfactant or elasticity, like shear elasticity. The moment you add any elastic stress that can generate gradients in tension, like Maragoni stresses, you kill the motility. Yeah.
Actually, I have a question. So with the local interactions between the rotors, is it attraction, repulsion, some mixture of the two? What's the right way to think of how the particles feel each other?
It depends on the relative orientation. So if you have, so I don't have the cartoon here, but imagine, like for example, it's easier. Let's look at rotors. Just like if you have another one here, the flow of this one is going to rotate it this way, right? If they're co-rotating, and the flow of this one is going to rotate it. This one it's going to move it upwards. So you can just look at the far field. So for the stresslet here, if you have another one here, it's going to be attracted. So it's going to be coming to it. But if it is located here, it's going to be repelled. So that's why the hydrodynamics makes things much more complicated because what they call it in physics, aligning, misaligning interactions, they really depend on where these particles are relative to each other.
Other questions?
Anyone excited about active matter now?
I think we all are.
It's a very rich field, and what I like about it is that there is room for, like a lot of physics, but also a lot of math. And I didn't even talk about the noise and, all the stochastic, models you can, build into. And, it would be really nice. I mean, I wish, I don't really want to create like what my student is working on right now. It's like a boundary integral method of the droplet with all the, whistles and bells of the particles interact with each other. If somebody can come up with some sort of a kind of maybe coarse-grained, continuum model of this internally fluctuating velocity field, how it's interacting with the boundary, it would be fun to, to look at it. Yeah.
I'm just curious for these, think of it as like a many-body problem. Are you using like fast multiple method and all these kinds of things? And if you are, like, how much work is it taking to do pure computational simulation?
A lot.
Yeah, right.
So the hydrodynamics, luckily, it's that because it's not only that it's many body interactions. I didn't emphasize enough, but this is a very confined system. So if you are, for example, in like the electrostatics and the hydrodynamics, if you think of it as point charges, dipoles, etc., not only they're interacting with each other, because you have all the images. So you have to sum up not only the direct interactions, but also the interactions through, and then hydrodynamics, these are not convergent. Like if you have to do it in a very smart way. There are very few people who have done the full hydrodynamics in confined. Alex Doneff actually has a very good code, and his student, postdoc Brennan Sprinkle. So I'm not doing the hydrodynamics, but the electrostatics surprisingly was not done. So we are trying to it actually is simpler because the sums converge. So we are working on adding the electrostatics to Brennan's code. So.
Great, thanks for sharing that.
Yeah. But also we don't know how to put the fluid boundary. So this is that's another beast.
I've seen similar talks, where it was instead of rotating things, it was much more like flappers traveling that ended up synchronizing. If you had certain numbers of distances, they had is there anything similar with spinny tails? Or sorry,
yeah.
Very formatted question.
No, it's a very good question. So that's another level of complexity, because here we just consider the very simple, there is no chirality. This particle doesn't have a shape. So now if you make it a sheet, I picture it, sorry about that, but I picture the stresslet like this, but it's essentially a singularity. So there is no shape. Once you throw the shape, it's another degree of freedom. There is the whole field of actually call it chiral active matter. So imagine that instead of having a sphere, but you have an ellipsoid or a dumbbell or they show a completely other stuff of self-organization. So yes, so shape does matter, and yeah, especially at zero Reynolds number.
All right, let's thank Professor Vlahovska again.
Thank you.